Let's get started with today's lecture. Quick lecture for today, just one section, and all we are focusing on is two new proof styles. The large one being proof by contradiction, the second one being, though, proof using what we call a contrapositive. So up until now in this course, when I ask you to prove something, you've so far been using what we call direct proof. When you're proving something, you always started, always and forever. What was the first line of your proof?
You assume your antecedent.
Assume your antecedent. Let alpha, whatever alpha is, and show that if alpha is the case, beta must also be the case. So I'm going to introduce you to another way that you can construct these proofs called the contrapositive first, where with the contrapositive, what you do is you start by assuming the not beta, and you show that implies not alpha. So first, let's really quick fill out this truth table showing that these two are logically equivalent, and then I'll give you an example for what I'm talking about. So going back to just regular Boolean algebra or Boolean logic. So filling this one out, we're doing the negation of alpha. So not true is false, not true is false, not false is, and not false is true. Let's write not beta really quick. Tell me what to write.
False, true, false, true.
Okay. Alpha implies beta. True implies true is.
True.
True implies false is.
False.
False implies true is.
True.
And then if they're both false, it's
True.
good. Now let's look at not beta implies not alpha. So I'm looking at this implies this. So false implies false is. True. True implies false is.
False.
False implies true is.
True.
And true implies true is.
True.
And notice, shock, those are logically equivalent. We've already seen this a couple times. Okay, so what? What does that matter for constructing proofs? So let's look at an example now, thinking about doing a proof using this piece of logic rather than using this piece of logic. So here's a proof we're going to do. Let R be an equivalence relation. First off, maybe let's say a little bit about equivalence relations. First off, remind me, what's a relation?
It's a set of ordered pairs.
It's a set of ordered pairs. A set where everything in it is just an ordered pair. Right? And we spent a lot of time talking about properties on relations. In particular, there's 5 properties that are all going to show up on your test. What are those 5 properties?
Reflexive, irreflexive, symmetric.
Irreflexive, symmetric, transitive.
Symmetric.
What did I miss?
I said anti-symmetric.
Oh, did you? And then
Anti-symmetric. Is that the one I missed?
And transitive.
And transitive. Okay, pretty sure we said them all. Now, what does it mean for a relation to be an equivalence relation?
It's reflexive, symmetric, and transitive.
It has 3 of those 5 properties at least. It's reflexive, symmetric, and transitive.
Can you re-say that part?
So if it's an equivalence relation, then that means it has the 3 properties being reflexive, symmetric, and transitive.
Okay.
If a relation has all 3 of those properties, then we say that that relation is an equivalence relation. We'll be saying that a lot, which is why I start using the E dot R dot for equivalence relation. Good so far?
Yep.
So let R be an equivalence relation on A. So A is a set that we're pulling everything out of. R is a set of ordered pairs, where everything in its ordered pairs comes from A. And R is an equivalence relation. So I know whatever it is, it's reflexive, symmetric, and transitive. With me so far? Okay, now let little a and little b be 2 things in big A. Pick 2 things out of the set, whatever they are. Our job is to show that if A is not related to B, then what is this?
That is the equivalence class.
That's A's equivalence class. What's an equivalence class of A?
Everything that's related to
It's everything related to A. If we were using the equivalence class, if A was a set of all students in this class, and R was a relation has the same last name, then my equivalence class would be everyone with the same last name as me, everyone who's a Timpson. Right? So what this is saying is that me and you don't have the same last name, then our equivalence classes have nothing in common.
Didn't we prove this already?
The intersection of our equivalence classes has nothing in common. I don't know.
Yeah, but
But-
we proved it going straight forward into the contrapositive.
Let's prove this now using the contrapositive. Let me grab my chair. So typically, before the contrapositive, how would you have started this proof?
You would have assumed that A is not related to B.
You would have started with 1, let or assume, however you want to say it, let or assume, same thing. You would have said assume A is not related to B. Okay, now how do you unravel that definition? What does it mean for A to not be related to B?
It means it's wrong.
It means it's not in the relation. That's kind of a harder thing to work with. So sometimes when you're going to do a direct proof, after you write that first line and you think about how can I unravel that definition, it's easy to get kind of stuck. If you feel yourself getting stuck, then rather than proving alpha implies beta, it's sometimes easier to just look at the contrapositive and show that not beta implies not alpha. So if I get stuck here, rather than saying assume A is not related to B, let's maybe instead assume not beta. So what was our beta in this statement? This statement is saying if A is not related to B, here's our alpha, then their intersection is the empty set. Here's our beta over here, right? So instead, I'm going to show not this implies not this. That's the exact same thing as showing this implies this. Showing alpha implies beta is the exact same thing as showing not beta implies not alpha. So what is not beta? What is a negation of A's equivalence class and B's equivalence class? Their intersection is empty.
Their intersection is not empty?
The opposite is their intersection is not empty. Sorry, was I pointing at the wrong one?
Yes.
Yeah. So what's the opposite of this? This.
Okay.
Their intersection is not empty. So let's start with that instead and see where we got. So let's say assume not beta. Assume alpha's intersection and beta's intersection is not empty. What does it mean for an intersection to not be empty? If I have two sets and they intersect, what does it mean for their intersection to not be empty?
But there has to be something in there.
There's something in the intersection. That's what it means for it to not be empty. So if alpha intersect beta is not equal to the empty set, then there exists X in A's equivalence class intersected with B's equivalence class. There exists something in the intersection. We're just calling it X. We can call it whatever we want. But since it's not empty, there has to exist something in there. What does it mean for X to be in the intersection of A's equivalence class and B's equivalence class?
It's an AN.
It means X is in A's equivalence class and X is in B's equivalence class. That's what it means for it to be in their intersection. It's in both. So I know X is in A's equivalence class and X is in B's equivalence class. Now what is A's equivalence class?
Everything related to
Everything related to A. So if X is in A's equivalence class, what does that mean?
X related to
X is related to A. And if X is in B's equivalence class, what does that mean?
X related to B.
X is related to B. Now, going from here to here, I'm just switching the order that I write this. How do I know I can go from X is related to A is related to X?
It's the equivalence relation.
It's the equivalence relation. In particular, it's
Symmetric.
symmetric. Since it's symmetric, X related to A gives you A related to X. Remember, symmetric means you can swap on both sides and it still works. If I have the same last name as you, you have the same last name as me. Okay, that's how we got from here to here. And then if A is related to X and X is related to B, A is related to B. What did I use there?
Transitive.
Transitive. And there we go. I just barely showed if we don't have this, then we don't have this. Where did I write that?
Okay.
You see how these short negations of each other?
Yes.
So rather than starting with this and ending with this, I started with not this and I ended with not this. And that's what the contrapositive is. So you can show alpha implies beta if you want. Sometimes it's easier to just show not beta implies not alpha. Good with that one?
Yep.
Okay. So now, let's introduce the third proof style. Proof by contradiction. Proof by contradiction. Intuitively, how do we do a proof by contradiction? If I show that it's impossible for a statement to be true, then it has to be
False.
false. Or if I show it's impossible for a statement to be false, then it has to be true. That's the intuition behind a proof by contradiction. So how do I show beta is true when I'm doing proof by contradiction? I show alpha and not beta implies something that is for sure false. If alpha and not beta is impossible,
It means the alpha and beta is true.
that means if the alpha is true, the beta must also be true. Because it's impossible for me to have alpha true and beta false. So I'm showing it's impossible for alpha to be true and beta false. Therefore, if alpha is true, beta has to be true. And that's what this is going to say. Alpha being true and beta being false implies something impossible. Now let's just write out the truth table for this to see if they're logically equivalent and then see it in a proof. So let's see, we're doing alpha and not beta. So alpha and not beta. So true and false is false. Implies false is
True.
true. You follow that one go?
Ah, got it. Okay, yep.
Remember, we're doing implies false at the end. Okay, so let's do the next one. True and true
It's true.
is true. Implies false is
False.
false. Okay. False and false is
Implies false, which is true.
false and false is false. Implies false is true. False and true is false. Implies false is,
True.
and what do you know? It's logically equivalent. So it's logically equivalent, showing alpha implies beta. It's the same thing to show alpha and not beta implies false, implies something impossible, implies what we call a contradiction. A statement that is always false, cannot be true.
Is there like a link between the two contras in contrapositive and contradiction?
Probably.
Does that come from a word or something?
I would assume it's because you're proving that beta, because you use a false beta.
I'm trying to remember
So it's contrary.
if this was somehow related to Aristotle's squares, but can't remember.
Okay.
So I guess that there's something in the etymology, just don't know what it is.
Thank you.
But yeah, maybe somehow tied to the fact that they're both using that not beta. Anyways, so now let's do a proof by contradiction to see this in action. So let's get started. If x is an integer, if x in the integers, if x is an integer, then x is not both even and odd.
Okay.
Tell me in words, what is our alpha?
X is in the integers.
X being an integer. So our alpha is saying x is an integer. What's our beta?
X is not even an
Not even and odd. So not both. I'll just write there to help us remember. So beta is not both even and odd. Okay. How does a proof by contradiction work? I need to show that alpha and not beta implies a contradiction. So I need to show alpha, which is x is an integer. And then what would not beta be?
If they are both even or
And both even and odd. I need to show that this implies something false. If I can do that, then we will have done a proof by contradiction. So assume, you're going to see this a lot, BWOC. You read that by way of contradiction. Let your reader know that this is a proof style that you're going to be using. Assume by way of contradiction that alpha, x is an integer, and not beta, x is both even and odd. With me so far? So I assume alpha and not beta. Now I need to show that this implies a contradiction. Okay, if x is both even and odd, x is even, right?
Yes.
What does it mean for x to be even?
It's equal to 2 times another integer.
It's divisible by 2, or in other words, then there exists a in the integers such that x equals 2a. If x is even, then it can be expressed as 2 times some integer. And if x is odd, what does that mean?
It's expressed by 2 times the integer of this one.
Right, and if it's odd, then there must also exist some integer, maybe the same, maybe different, such that x is equal to 2 times that integer plus 1. That's what would mean for x to be odd, that's what would mean for x to be even. So if x is equal to 2a, and x is equal to 2b plus 1, then 2a is equal to 2b plus 1, since they're both equal to x.
Yep.
Okay, subtract 2b from both sides. Good.
Yep.
Divide both sides by 2.
Uh-huh.
Good. And so what do we have? I have an integer minus an integer is equal to 1/2.
Which is
But I know that an integer minus an integer is always and forever a
integer.
integer. So I know an integer minus an integer is in the integers, that's an integer. And I know that an integer minus an integer is equal to 1/2, which is not an integer. So an integer minus an integer is an integer, and an integer minus an integer is not an integer. Can both those things be true? No, that's impossible. So that's when we write the contradiction symbol. What is that? That's an arrow pointing this way and this way. So I'm writing an arrow pointing that way together with an arrow pointing this way. That's what that symbol is. And that's your symbol for telling the reader what you just read is a contradiction. It is impossible for it to be true. It is always false. It's this thing right here. That's our always false statement. Therefore, x is not both even and odd. Therefore, we can conclude our beta. So alpha implies beta is what we just read showed there. Let's do another one. Proof by contradiction once again. If A and B are in, have we talked about this one, this set? The real numbers. So that fancy R means all real numbers, pretty much anything you can think of as a number. So pi's in there, the square root of 2's in there, etc. So if A and B are in the real numbers, where A is not equal to 0, then this equation, ax plus b equals to 0, has at most one solution. Okay, once again, what's our alpha?
If A and B are in the reals.
Alpha is A and B are in the reals,
And not 0.
where alpha is not equal to 0.
A is not equal to.
Where A is not equal to 0, thank you. And then what is our beta?
The A plus B has one solution. Most solution.
Ax plus b equals 0 has one solution at most, right?
Yeah.
What would be the negation of beta? So what would be not beta?
Yeah, I have 2 or more solutions.
Yeah, that would be ax plus b equal to 0 has 2 or more. The number of solutions is greater than or equal to 2. Right? 2 or more solutions. This is just a scratch word to help us think about it.
Yeah.
So in doing a proof by contradiction, I need to show alpha and not beta implies a contradiction. So up here, I wrote the alpha and the beta on the same line, just to try and make it read more like this. In practice, what we typically start by is first, we assume alpha as our first line, and then we put the not beta on the second line.
Okay.
But the exact same thinking. So let A, comma, B in the real numbers. Let A and B be real numbers where A is not 0. All I did there is wrote alpha. Assume, by way of contradiction, that not beta. Assume, by way of contradiction, that ax plus b equals 0 has at least 2 solutions. That's the negation of it having at most 1. Because there's no such thing as having 1.5 solutions.
Right.
So if you have more than 1 solution, you have at least 2. You could have also said more than 1 solution. That would have worked fine. Okay, so there is our not beta. So here we just really wrote not beta. Okay, now what? Well, if it has at least 2 solutions, what does it mean for x to be what's a solution to an equation like this? Let's write out a concrete case of one of these equations. If I wrote something like 4x plus 2 is equal to
0.
30. Oh, it has to be equal to 0, doesn't it?
Yeah.
Equal to 0. What is a solution to this equation?
1/2.
Almost, not 1/2.
-1.
Minus 1/2. Minus 1/2 is the only x you can plug in to make that true.
Yeah.
So this one has only one solution, namely minus 1/2. Okay, pick some other equation. What if right there I would have put a minus 2x plus 78? Maybe that equation is going to have more than one solution. Okay, that one only has one solution. Try another one, try another one, try another one. Will it ever be possible to come up with one of these equations that has 2 or more solutions? We're going to prove that that's impossible. That it has at most one solution. You with me? Okay. So, that's what we're going to do. So, assume by way of contradiction that we found some numbers, A and B, where it has at least 2 solutions. Well, if it has at least 2 solutions, one of the solutions we're going to call x1 and one of the solutions we're going to call x2. So then there exists x1 and x2 in the real numbers such that ax1 plus b equals 0. In other words, x1 makes the equation true. And ax2 plus b equals 0. Or in other words, x2 makes that equation true. Where x1 and x2 are actually different numbers. You didn't just plug in the same number twice.
Right.
So we found 2 different numbers that satisfy this equation. Not satisfy this equation, sorry. So then, if ax1 plus b equals 0 and ax2 plus b equals 0, then ax1 plus b must equal ax2 plus b, because they're both equal to 0. So those 2 equations have to equal each other, because they're both equal to 0.
Right.
Subtract b from both sides. Divide both sides by a. How do I know I can divide both sides by a?
That's just what they would do. Okay.
What's the one time you can't divide by a number?
Zero.
If it's 0, that's why we had to specify a not equal to 0. That was an important piece of information. So now we can divide both sides by a since a is not 0.
If A was 0, wouldn't it?
Then that's an undefined operation.
But if A is 0, that's just 0 equals to 0, isn't it? Or B equals to B. Because 0 times anything is 0. So.
But then you would no longer be forced to say that x1 is equal to x2. Let me give you a concrete example. So where a is allowed to be 0, 0 times x plus 6 equals 6. How many solutions does that have for x? If only many. But if we require a is not equal to 0, now we're proving it has at most 1. Okay, so since a is not equal to 0, divide both sides by a, and I get x1 equal to x2. So then, x1 is not equal to x2, and x1 is equal to x2. Of all the statements out there that I know are for sure false, that's one of them. Hard to be more false than that.
Yeah.
So what did we just really show? We showed alpha and not beta implies something false. Therefore, beta cannot be false. So beta has to be true. Therefore, there is at most one solution. Good? These proof by contradictions, they take a sec to get comfortable with. The logic behind them seems a little bit scary, but the intuition for it, once you start proving them, kind of just falls into place. And it feels natural enough. So I feel like enough examples and you'll just feel comfortable with it. And I should specify, this isn't going to be like other sections where, you know, we count, we handle this for a while, then we move forward. Proof by contrapositive and proof by contradiction, these are things that we will use throughout the class forever now. And if you go on to take more advanced math courses, you will use these proof styles 100 times. They will never go away. These are very useful proof tools. Do we have everything on the board? Just make sure I can see the edge. Okay, so let's do one more proof by contradiction and then we'll do our test. So our next proof. 2 consecutive integers cannot both be even.
Oh.
That makes sense.
2 consecutive integers cannot both be even. What are 2 consecutive integers?
So x plus 1.
Yeah.
Well, in general though, but I mean concretely. 8 and 9. There's 2 consecutive integers, one after the other. If this one is even, that one cannot be even. That's what we mean by 2 consecutive integers cannot both be even. If you were to count the numbers, 1, 2, 3, 4, you would never list an even followed by an even. How can we prove that? Maybe when you get way up there, suddenly there's 2 evens next to each other.
Well, the definition of the number and then the definition of even odd is how you prove it. So
Yeah,
eight
I
is
feel like you could do it.
1 plus 1 plus 1 until you get to 8, and that's even. And then the definition of odd is 2 divided by 8 divided by 2 or whatever.
You got the right idea. The definition of odd is kind of like the definition of even, but adding 1. So if you start with an even and yet add 1, it's going to force you to be in an odd.
Yeah.
And that's exactly the thinking that we're going to use in this proof.
So that doesn't have to be a contradiction proof if you don't want it to be. You can use it right proof for that, right?
You will never have to use a particular proof style. It's just, is it easier for you to think about that way? And oftentimes it is going to be easier to think about it as a proof by contradiction than otherwise. Okay, now, sometimes you might get stuck on a statement. First, always, and forever. What's the first thing we do? We got to think about it as an implication. So we got to think about this as alpha implies beta. So this line right here is just me reworking it how you would have thought about it in your head. What is that statement saying? It's saying if x and x plus 1 are 2 consecutive integers, then they are not both even. Right? Okay. So let's assume our alpha. So let x be an integer where x and x plus 1 are consecutive integers. There's let alpha, or assume alpha. Good so far? Now we're going to assume by way of contradiction, not beta. So what is our beta?
That they're not both even.
They're not both even. So what's the negation of that?
They are both even.
They are both even. So assume by way of contradiction that x and x plus 1 are both even. Now, if x is even, what does that mean?
It's equal to 2 times the integer
It can be written as 2 times an integer. So then there exists a in the integers such that x is equal to 2a. Well, if x is equal to 2a, what's x plus 1 equal to? Then x plus 1
It's 2a plus 1.
is 2a plus 1.
Which is
Which means that x plus 1 is odd. That's the exact definition of odd. What would we just barely prove in the previous proof?
That they can't both be even odd.
Something can't be both even and odd. So then x plus 1 is both even and odd, which is impossible by the previous proof. Therefore, 2 consecutive integers cannot both be even.
Okay.
Good?
Yep.
Okay, so there's a couple examples with that. Any questions you want recorded before we move on to the test?
How many more proof styles are there?
Sorry, what?
How many more proof styles are there?
There's some, I don't want to say here's how many proof styles there are, but as you get into a particular field, sometimes there are unique proof styles that come up. You've already seen, I think, proof by induction. That's a common one. But then you can get very niche ones. If you remember all the way back to computation theory, we use something called the pumping lemma over and over again to help prove something.
Oh, like pigeonhole and stuff like that?
Pigeonhole's another one that comes up. So there are, I don't want to say here's the number of proof styles there are.
Alright.
Okay, but these 3, well, direct proof obviously, but these other 2, contrapositive and contradiction, they're ubiquitous. They're everywhere. Any textbook you pick up, you'll use these. Even that little bit that I was teaching the geometry students, proof by contradiction was a natural choice for some of those proofs.
Yeah.
And if some of you who took geometry from me, you might remember early on we said, why is this picture impossible? That was the same thing as proof by contradiction.
Right.
So they didn't get all this logic written out for them so that they could see it like that, but that's what it is. Okay, anything else? All right. Those tests should be printed.